Hello and welcome back to another YouTube video, and today we're going to solve a LeetCode problem called insertion into a binary search tree. We're given a root tree node, a root reference, which is just basically a tree, a binary search tree, and an integer, and this integer we want to add it in that tree without losing the binary search tree property. Binary search tree property is its left child is always greater than its parent, and right child is always left child is smaller than its parent, and right child is always greater than its parent. So we need to keep the BST property. So how can we do that? Alright, so that's a problem, and I will give you a conceptual overview so we can have better understanding of this problem. Alright, so right now we have a position at the root. We have reference to the root of the binary search tree, and we want to add a value. For this example, I'm giving 25. We want to add 25 in this BST while keeping its property. So where could we add this BST? A position, we can add it here. For example, we can add it like after 10, like between 10 and 27. We can add it here and then will work just fine. There would be no problem. But there are also other places we can add it. We can add it at the right side of 20. After, if we added it at the right side of 20, it keeps the BST as well. So there are multiple solutions to this problem, but for me, I find the most optimal solution is considered like searching for this binary search tree until we find a specific location to add. So for example, here I'm just gonna check like a normal search, like is 25 greater than 10? It's greater than 10. Alright, then we move right. We go to 27. Is 25 greater than or smaller than 27? It's smaller than 27. Alright, go left. Now we're at 14. Is 25 greater than or smaller than 14? It's greater than. Then we go right. Now we are at 20. Is 20 greater than or smaller than 25? 25 is greater than 20, so we go right. But there is no right, so basically we just add it here. And boom, we have solved our problem. This is the solution I'm gonna do, and it's a really straightforward solution. Alright, so let's speak about complexity of this algorithm. There is two ways of doing this algorithm. One is iterative way, and one is other is recursion. I myself prefer iteration because of its space feature, which is no extra spaces, since we're just using the same tree without making any extra data structure. Or maybe if you want to use a recursion approach, you will probably use O space of log n, which is the backstack memory of recursion calls of the being called. So this is for the space complexity. For the time complexity, we're using approximation of 3 to 4 calls just to make the insertion process. So the algorithm runs in time of O log n, where n is the number of nodes. So if we went back and checked how many steps we have taken, we taken 1, 2, 3, 4, and we added in the fifth added the element in the fifth step. Actually, at the fourth, like when we are at 20, then we are checking if there is element. So it's 4 steps. So that's approximation of log n. So the time complexity for both iteration or recursion is O log n, but for space complexity, in iteration O of 1, recursion O of log n. And that's it for the complexity. Let's check the code.